Chapter 9, Sampling and Distributions. Section 9.1, Sampling Variability and its Annoyances. Imagine you are a data scientist and are hired by a fitness company to determine whether men or women are more likely to exercise at certain times of the day. Wouldn't it be easy to find one man and one woman and ask about their preferred workout times? Sure, yeah, that would be easy, but the data would not be generalizable. Why not? Of course you know why not. Individuals have different preferences and time constraints. There might be some sex differences on aggregate, but not every man or every woman has the exact same preference. Okay, fair enough. So you decide to sample 1,000 men and 1,000 women for a total sample size of 2,000. You compute means and standard deviations, but then your dog eats the raw data. And shame on you for not backing up the raw data, but that's a different topic. So, you need to collect a new sample of 2,000 different people. Do you expect those means and standard deviations to be identical to the first sample? It is reasonable to expect the descriptive statistics to be similar, but you would not expect the results to be exactly numerically identical. This is because of sampling variability. Sampling variability is the fact that different samples, even from the same population, will have descriptive statistics with different numerical values. In other words, there is variability across samples. This is not the same thing as variability within one sample, as measured by the standard deviation. The distinction between variability within a sample versus across samples has implications for parameter estimates, inferential statistics, and confidence intervals. Within versus across sample variability is also the basis for ANOVAs. Now, you'll learn about these topics later. For now, I want to make sure the idea of sampling variability is clear. Different samples, each of which comprises many individuals, can have different descriptive statistics. So, in other words, sampling variability means that different samples from the same population can have different values of the same descriptive statistic. Sampling variability is annoying because it reflects variability at a separate level from what we've considered before. Recall that the motivation for measuring a sample instead of one individual is that one individual may not be representative of the population. That's why we trust the average of a sample more than we trust a single data point. But now I'm telling you that a larger sample might not be reflective of the population and that the answer to your research question might change across different samples, not just across different individuals within a sample. Footnote. Note on terminology. As a noun, sample is used both as an individual data point and as a group of data points. As a verb, sample refers to the process of obtaining one or more data values. I will use sample to indicate a collection of data points, but you will need to infer the meaning from context in other resources. Margin note. Implication of sampling variability. A single measurement or sample is not guaranteed to be a reliable estimate of a population parameter. Back to the text. In other words, sampling variability is annoying because it means that although we can trust a sample more than an individual data point, we still cannot completely trust a sample solely because it contains multiple data points. I hope you have the intuition that larger samples should suffer less from sampling variability than smaller samples. That is, descriptive statistics of a sample with n equals 10,000 are more likely to be similar to each other than those of samples with n equals 10. That intuition is codified in the law of large numbers, which you will learn about later in this chapter. Section 9.1.1, an example with random data. Consider the experiment summarized in figure 9.1. I created 50 samples, each comprising 500 random values. Although the general characteristics of the samples were similar, the exact distributions and means were different. Indeed, even the mean of means, that is, the average of the 50 sample means, was not exactly 0, which is the population value. This paragraph refers to figure 5.1, which illustrates 50 samples of random Gaussian distributed numbers that are visualized as histograms in panel A and a scatter plot of the sample means in panel B. So panel A shows histograms for each of the 50 samples, which each sample corresponding to a dot with a different color. And we see that the average of those histograms shows a fairly nice looking Gaussian curve in a black line. In panel B, we see a scatter plot of the sample means. So the x-axis shows the sample number ranging from 0 to 49. The y-axis is the mean of each sample, and the square, the gray shaded square, for each sample corresponds to the mean of that sample. We also see a dashed horizontal line corresponding to the mean of the sample means, which is minus 0.0101. That's slightly different from the true population mean of 0. Section 9.1.2, where does sampling variability come from? Sampling variability has a negative impact on the reliability of parameter estimates and statistical inference. Therefore, it is useful to understand where sampling variability comes from and to consider whether you can reduce this variability. Natural variation. Variability is common in datasets derived from biology, from cellular neuroscience to psychology to medical treatments to cultural practices. There is a natural variation in genetic and environmental factors that cause different people to react differently in the same situation. This variability has two implications. One, different samples are likely to have different characteristics. And two, samples from different ages, genders, economic ladders, or cultural backgrounds are even more likely to differ. But natural variation also exists in non-biological samples, for example, earthquake magnitudes, the number of stars in each galaxy, and heights of buildings in a city. Measurement noise. Measurement sensors are imperfect and introduce variability due to noise. Dynamics and changes. Nature is impermanent. The same measurements of the same system might differ over time simply because that system has changed. Opinions about geopolitical events are one example of how repeated measurements can differ. Complex systems. Most objects of scientific investigation are complex. That's because most simple systems are already figured out or are not that interesting to study. Whereas most experiments are designed to simplify, reduce, or ignore complexity. For example, repeated samples about gym time preferences that ignore the time of year will have higher sampling variability. Stochasticity or randomness. There is randomness in the universe that we cannot measure or do not understand. On a microscopic scale, you can think of Brownian motion. On a macroscopic scale, you can think of changes in weather affecting our decisions. Which factors will be larger sources of variability and which can you control or at least measure? The answers to these questions are specific to each research project, so I cannot provide general conclusions. But these are questions that you should consider before embarking on any research or statistical adventure. You should strive to reduce sampling variability without making the sample so homogeneous that it compromises generalizability. Section 9.2, Creating Sample Estimate Distributions. Let's say we take k independent samples from a population. Each sample is called S, and so the ith sample is called S sub I. Because these are independent samples, each sample can have a different sample size. Each sample has its own average value, which we'll call S sub I bar. This means that k samples will produce k average values. This scenario is depicted in figure 9.2a. Figure 9.2a shows a data table where the columns correspond to samples S1, S2, and so on up to Sk. The rows indicate data points, and there are just asterisks inside circles to abstractly depict data values. And then we see towards the bottom, first of all, that the columns have different numbers of rows, indicating that not all samples have the same sample size. And at the bottom of the table, in the final row, we see arbitrary symbols indicating the average value from each data sample. The concept depicted by this data table is that you can have samples of different sample sizes, but each sample has one average value. Back to the text. So each sample S sub I has a data distribution which we can represent using a histogram. Because these samples are from the same population, we can expect the distributions from repeated samples to be similar. But because of sampling variability, we do not expect the histograms to be identical, especially if the sample sizes are small. Thus, figure 9.2b shows k histograms coming from k data samples. The stars indicate the mean of each sample. So, figure 9.2b illustrates histograms. We see many histograms. I think there are 50 histograms shown in thin gray lines, and what you can see is that they are all somewhat similar. They have similar characteristics, similar skews, but they are distinct histograms. There are asterisks drawn on top corresponding to the mean of each distribution. Back to the text. The sample means, on the other hand, form a collection of k values, and we can produce a histogram of those k sample means. This histogram is not computed directly from the raw data, but instead comes from the descriptive statistics that were computed from each individual sample. This paragraph references figure 9.2c, which shows a histogram of the means of each sample that were depicted as asterisks in the histograms in panel B. Panel C also shows the average of all the data histograms. And what you see in this panel is that the average histogram is very different from the histogram of the sample averages. The sample averages appear to be somewhat uniformly distributed between 0 and 5, whereas the average of the data histograms look like a F distribution, or like a Gaussian with some skew, some positive skew. Back to the text. Important note: the distribution of sample means is not the same as the average of the sample histograms. In fact, they can have completely different shapes. You will see more examples of this in the section on the central limit theorem. Why are sample distributions important? Among the reasons are that they reveal insight into the variability in the population and that they are used to compute confidence intervals. The depiction and discussion in this section concern the average value, but you can also compute sample estimate distributions for any descriptive statistic, including standard deviation, median, correlation coefficient, and so on. Section 9.3, Standard Error of the Mean. Here's a conundrum. The sample mean is an estimate of the population mean, but different samples have different sample means. So how precise are those estimates? In other words, how much uncertainty is associated with the sample mean as an estimate of the population mean? That is the question that the standard error of the mean addresses. The standard error of the mean, often abbreviated to SEM, is a descriptive statistic that you compute from one sample, and it estimates the precision with which that sample mean estimates the population mean. In other words, the SEM is the amount of variability that can be expected in the means of repeated random samples of the same sample size from a population. It is defined as the population standard deviation scaled by the sample size. Here we have equation 9.1, which reads SEM equals sigma divided by the square root of n. Sigma is the true population standard deviation, and n is the sample size. I hope this formula makes intuitive sense. Our certainty about estimating the population mean from a sample increases with increasing sample size. So, that is, as n increases, remember n is in the denominator, so as n increases, the SEM decreases, indicating that the sample mean is a more reliable estimate of the population mean. An SEM will also decrease with standard deviation. That is, the more homogeneous the population, the more accurately we can estimate its mean with a sample. In practice, we don't know the population standard deviation, and so instead we estimate the SEM using the sample standard deviation. Here we have equation 9.2, which reads SEM is approximately equal to S divided by square root of n, where S, as you know, is the standard deviation of the sample, which we assume is a good estimate of sigma if the sample is random and representative, and if the sample size is sufficient. Section 9.3.1, Standard Error of the Mean versus Standard Deviation. Standard deviation and SEM are conceptually similar in that they quantify variability associated with a sample dataset. They are also mathematically similar, as one is simply a scaled version of the other, but they reflect different aspects of uncertainty and have different interpretations. These distinctions are described below. Conceptual meaning. Standard deviation quantifies the spread of the values around the mean of the sample. SEM, in contrast, quantifies the precision of the sample mean as an estimate of the population mean. Essentially, it tells us how close our sample mean is likely to be to the unknown population mean. Another way to think about the distinction is that the standard deviation reflects the observed variability within a sample, whereas the SEM reflects the expected variability of means across different samples. Calculation. Standard deviation, as you know, is calculated using each data point within a sample and is defined as the square root of the average squared distances from the sample mean. SEM is the standard deviation divided by the square root of the sample size, so the assumption is that the sample mean is just one of many possible sample means that could be measured from the population. Now, the reason for dividing by n instead of n-1 is that the SEM is not a descriptive statistic of a sample, but instead is an estimate of the uncertainty with which the sample mean reflects a theoretical distribution of many sample means. Applications. Standard deviation is used as a measure of variability within a data sample and in transformations such as z-scoring. SEM is used in generating confidence intervals and to evaluate statistical significance of test statistics like t-values and regression coefficients. Impact of sample size. The standard deviation does not change with the sample size. To be sure, larger samples can provide more accurate estimates of the population standard deviation, but the standard deviation does not trivially increase with sample size because the division by n-1 balances the summation in the numerator. On the other hand, the SEM decreases as the sample size increases even if the standard deviation does not change. Indeed, the population's standard deviation does not change as a function of sample size. Section 9.4, Random and Representative Sampling. The entire purpose of inferential statistics is to evaluate whether the characteristics of one sample will generalize to a population. Ergo, it is important that the dataset is generated from random samples that are representative of the population to which you wish to generalize. Representative samples. Let's say we have a dataset of how much money American households spend on junk food each year. Can we use this dataset to predict the mass of stars within a certain radius of a black hole? Wait, what? That is a crazy question. Obviously, the answer is no. And the reason is that the dataset, American household spending, is not representative of the population we seek to understand, star masses. Okay, that was too extreme an example. How about this one? Let's say we have a dataset of university students' views on universal basic income. Footnote. Universal basic income is an economic program in which all residents in a geographical area receive a guaranteed income, for example, from the government and funded by taxes. Back to the text. Can we use this dataset to infer how all people view universal basic income? No, because university students are not representative of the entire population. Most university students have age, education, and socioeconomic characteristics that differ from those of the entire population. On the other hand, it is reasonable to expect that results from that dataset will generalize to other samples of university students, possibly at other universities and possibly in other countries. Now consider those same university students, but this dataset is from a visual perception task in which the students had to match two 3D rotated shapes. Would these data generalize to all people? It is more reasonable to expect that low-level visual perception is less impacted by education level. Anyway, the point of these examples is that results from sampled datasets can generalize to a larger population only if those samples are representative of the population. Sometimes it's easy to determine whether the samples are representative, while other times it requires careful thought and perhaps additional research. Random samples. Random sampling is one way to help ensure that the sample is representative. Your data collection should ideally come from randomly sampled individuals. Let's reconsider the universal basic income example. Imagine that all of these surveyed students were enrolled in a course entitled Economic Fairness at a liberal arts college. Their opinions are likely to differ from the population of all university students. On the flip side, students enrolled in a course entitled Taxes and Capital at an elite business school are equally unlikely to have opinions that are widely shared by the entire university population. I'm sure you see the problem with datasets that are not representative of the population to which you want to generalize. The solution is simple. Always collect a dataset in which the samples are randomly drawn from the entire population that you wish to generalize. Footnote. In truth, random sampling per se is not important. It's merely a way to help ensure that the sample is representative. If you are an experimental particle physicist, you can non-randomly select helium atoms to study because all helium atoms are the same and therefore representative of the universe's population of helium atoms. Margin note. Random sampling. Each member of the population has an equal chance of being in the sample. Back to the text. Okay, all that said, let's bring this discussion down to reality. It's very easy for me to sit up here on my high horse and lecture about the importance of random and representative sampling. Reality is more difficult and more subtle. Where do you get your research participants? Do you offer money? In which case, you are selecting people who need money and have enough time. Do you offer course credit? In which case, you are probably selecting psychology students. Do you recruit from the supermarket during the day? In which case, you are selecting people who are retired or do not have wage jobs. Do you randomly dial phone numbers? In which case, you are selecting people who have a landline and are at home when you call. Do you post an ad online? In which case, you are selecting people who visit whatever website you advertise on and have the time and interest to click through. I could go on, and these were just some examples involving human research participants. Any other branch of empirical science faces the same issues. The point is that gathering data randomly from representative samples is a goal to strive towards, but in reality can be difficult to achieve. So how do you evaluate whether your sample is random and representative? Unfortunately, there is no formula or algorithm that gives an answer. You need to critically and carefully evaluate each experiment and each sample. If possible, you can compare the descriptive statistics of your sample with known population characteristics. For example, you can compare the age, gender balance, and years of education in your sample to those of the population. If those basic characteristics match, then you can have more confidence that the research findings will generalize. There is a silver lining to this statistical rain cloud. If individual samples are biased, but different samples are biased in different ways, then averaging sample means can, to some extent, compensate for the biases. More on this in the section on the law of large numbers. Section 9.4.1, Independent and Identically Distributed Data. IID is a technical term that is used in math-heavy discussions of statistics. IID, or Independent and Identically Distributed, provides a deeper definition on the random part of random and representative data samples. According to IID, data in a sample should be independent, where independent means that each data point is unrelated to other data points. For example, randomly sampling people according to the final digit of their social security number would ensure independence, whereas sampling people from the same household would cause dependence. Identically distributed. This means that all data are drawn from the same distribution. Mixing data from different distributions, for example, normal and power law, would mean that their descriptive statistics were mixed and therefore more difficult to interpret. In empirical data, this assumption is difficult to ensure or to evaluate, but gathering all of your data in the same way will help maintain this assumption. Section 9.5, The Law of Large Numbers. Sampling is done by practical necessity, not because it's the best thing to do statistically. If you want to know how much penguins weigh, it would be ideal to measure every single penguin in existence. Now, I suppose that would, in principle, be within the realm of human possibilities, but it would cost such a huge amount of time and money that it wouldn't be worth it. And that is why we sample. It should be intuitively sensible that because of sampling variability, larger samples will more accurately reflect the population characteristics. The math behind that intuition is codified into the law of large numbers, which is often abbreviated LLN. The LLN is formalized with a mathematical expression, which I will present here and explain below. Equation 9.3 reads the limit as n goes to infinity of p to the absolute value of x sub n bar minus mu and absolute value is greater than epsilon n parenthesis for the p equals 0. So the first term, limit, indicates the limit as the sample size n increases to infinity. Footnote: the infinity is for pure math, not for literal interpretation. If the population is large but finite, for example, the number of Paraguayan citizens in 1950, then you can think of replacing infinity with the population size. End footnote. The absolute value term indicates the magnitude of the difference between the sample mean for a given sample size, so that is x sub n bar, and the true population mean, which is mu. The epsilon is a Greek letter, and it's often used in calculus to denote an arbitrarily small number. Equation 9.3 can be read out loud as the sample size gets arbitrarily large, the probability that the sample mean is appreciably inaccurate goes to 0. In other words, larger samples more accurately estimate the population mean. As n approaches the population size, the sample will necessarily be representative of the population. But for smaller sample sizes, equation 9.3 relies on the assumption that the sample x is representative of the population. Section 9.5.1, LLN and sample size. This is the law of large numbers, demo number 1. Let's run a demonstration using simulated data because we can produce the entire population and therefore know the true population mean. I've repeated the sequence 1, 2, 3, 4 many times to produce a population with 4,194,304 data points and an exact population mean of 2.5. Then I computed the mean of random samples of sample sizes ranging from 1 to 1,500. Figure 9.3 shows the sample means plotted as a function of the sample size, with the horizontal black line indicating the true population mean, mu. This paragraph references figure 9.3. Figure 9.3 shows a demonstration of the law of large numbers in simulated data. It is a scatter plot in which each square is the average of a sample of size corresponding to the x-axis value. There is a horizontal line at the y-axis value of 2.5, indicating the true population mean. The sample sizes on the x-axis range from 1 to 1,500. And what you can see in the plot is that there is kind of like a funneling where the sample averages associated with small sample sizes to the left of the plot are a little bit more distributed, and they quickly taper into the population average as you go to the right with larger sample sizes. That said, you never get exactly 0 variability. There continues to be some variability of the sample averages around the population average. Back to the text. I have 4 observations about this demonstration, which reveal important insights into the nature of inferring a population parameter based on sample statistics. Before reading the text below, I encourage you to make your observations based on that figure. Observation 1. The sample means do not exactly equal the population mean. They do seem to be quote-unquote close to the true mean, but that judgment is just based on the y-axis scaling. The discrepancies would actually appear larger had I zoomed in on the y-axis. This is something you can try in the online code. Observation 2. The discrepancies from the population mean appear to be unbiased. That is, the sample means are sometimes less than and sometimes greater than the true population mean. Observation 3. The variability of the sample means decreases with increasing sample sizes. Notice the quote-unquote pinching of the sample means with increasing n. Observation 4. Even up to n equals 1,500, the sample means do not exactly equal the population mean. This is remarkable considering that the entire population comprises only 4 possible values: 1, 2, 3, and 4. Section 9.5.2, the Law of Large Numbers and Repeated Samples. This is LLN demo number 2. The LLN is often used in the context of sampling distributions. The idea is that any one sample or any one experiment is sensitive to sampling variability, noise, and other sources of non-systematic variation. This means that one sample or one experiment is unlikely to provide a good estimate of the true population mean. Therefore, instead of considering the means of individual samples, we can consider the average of sample means. To demonstrate the power of computing the average of sample means, I modified the previous demo. The population was the same, but now I took 50 samples, each of size n equals 30. That's much smaller than most of the sample sizes in the previous demo. Figure 9.4a shows the individual sample means, and here's the key novelty of this demo. I computed the cumulative average of the sample means in figure 9.4b. For example, the data value at x-axis location s equals 10 is the average of the means from samples 1 through 10. This paragraph references figure 9.4, which demonstrates that the cumulative average of sample means converges to the true population mean. There are 2 panels, panel A on top and panel B on the bottom. Panel A shows a scatter plot of each sample mean. The x-axis goes from 0 to 49, indicating the 50 samples that I drew from the population, and each square in the scatter plot depicts the sample mean from each sample. There's a horizontal black line at y-axis value of 2.5, indicating the population mean. These sample means are kind of scattered around the true population mean, similar to what figure 9.3 showed. Panel B shows the cumulative sample means, where the x-axis now indicates the samples, but it's the cumulative average from the first sample up to each current sample. Underneath the S equals tick marks is an N equals tick mark. So this illustrates, for example, that when S equals 20, we have the cumulative average of the previous 20 samples means, and that gives a total sample size of 600. So N equals 600 when S equals 20. What you see in panel B is that the variability across the different samples over the x-axis is much, much smaller, and the sample means, the means of the samples, converge to the true population mean very, very quickly. Back to the text. Again, a few observations. Observation 1, the individual sample means were distributed around the true mean, panel A, same as in the previous demo. Observation 2, the cumulative average converged to the true population mean after only a small number of samples. That's quite striking. Why did the cumulative average of small n samples converge to the population mean after only a few samples? The key insight is that individual samples have more variability than the sample means. So the SEM is smaller than the standard deviation, so the average of repeated sample means, which was shown in panel B, has higher precision than the average of individual samples, which is depicted in panel A. Consider figure 9.5, which depicts a population of data with 2 variables. The randomly selected data in blue circles and red triangles are distributed throughout the entire data space, but both sample averages are close to the center of the data space. This illustrates the concept that individual samples have more variability than sample averages for the same reason that the SEM, the standard error of the mean, shrinks with increasing sample size, whereas the standard deviation is unaffected by sample size. This paragraph references figure 9.5, which shows an illustration of why sample means have less variability than individual samples. We see a two-dimensional scatter plot with variable 1 on the x-axis, variable 2 on the y-axis, and white squares that are uniformly distributed all throughout space. We are depicting two samples being drawn. Sample 1 is indicated as blue circles that are just randomly chosen subset of the white squares, and sample 2 is indicated with red triangles. Again, these are just randomly selected samples from the entire space. And then we see towards the center of the plot a large blue circle and a large red triangle indicating the sample means. And the point here, the key point, is that the population data are distributed. These samples, the individual random samples, are also as distributed as the population, but the two sample means are very close to each other towards the center of the plot. Back to the text. There is an even more important implication of averaging over samples. In the real world, collecting huge sample sizes is often infeasible. Much more common are studies with sample sizes that are constrained due to limited funding or time. Therefore, combining data across multiple independent studies can provide a more accurate assessment of the true effects. This approach is called a meta-analysis and is particularly important for medical research. On the other hand, individual samples collected by different research groups may contain biases due to non-representative samples, poor experimental design or equipment, or human mistakes. You might wonder whether it's a good idea to include research that contains such biases. As long as the biases themselves are not the same in every sample, the LLM helps ensure that the sample means can be combined to get a more accurate estimate of the true population mean. Imagine that we collect 6 samples from the data shown in figure 9.5, except that each sample is biased, figure 9.6. Individual sample means are not accurate approximations of the population mean. However, because individual sample biases are random across the different samples, the average of sample means is an accurate estimate of the population mean. This paragraph references figure 9.6, which illustrates how averaging across sample means can compensate for biased sampling from different individual studies with sampling biases. This is, of course, assuming that the biases are independent of each other and distributed over the entire data set. We see a two-dimensional scatter plot similar to what I just described for figure 9.5, except here there are 6 samples drawn instead of 2 samples as in figure 9.5, and these samples are not randomly drawn, they are drawn as diagonal stripes across the XY plane. So each individual sample is biased, but because the biases are randomly distributed throughout the population, the average of the sample means, which is indicated in the plot as a large black circle, is still an accurate representation of the average of the population, which is corresponding to the center of this graph. Back to the text. For this reason, data from multiple small-scale studies can be combined to produce better estimates of population effects. Again, this highlights the value of meta-analyses in medical and psychology research. Final thought for this section. Have a careful look at the sample means in figure 9.3. They are distributed above and below the expected value, and it seems like there are fewer sample means far away from y equals 2.5 and more sample means closer to y equals 2.5. In fact, we could think of creating a histogram of those sample means and ponder the shape of their distribution. Segue to the next section. Section 9.6, the central limit theorem. The central limit theorem, abbreviated CLT, states that a distribution of sample means tends towards a normal distribution, even if the original variables are not normally distributed. The CLT is important because it helps ensure the validity of assumptions that we use in inferential statistics. I will first go through a few demonstrations of the CLT and then explain the implications. Section 9.6.1, CLT Part 1, Sampling Distributions. I created a population dataset of integers 1 through 6 using probabilities from the biased die in Chapter 8. Remember that the sides 1 and 2 have probability of 1/4, and other sides have probability of 1/8. Figure 9.7a shows the histogram of the population data. I next drew 500 random samples, each of size n equals 30, and stored the mean of each sample. The histogram of those sample means is shown in figure 9.7b. This paragraph references figure 9.7, which shows a distribution of population data and 500 sample means. There are two panels, panel A and B. Panel A on the left shows a histogram of population data. There are 6 bars in this histogram corresponding to the 6 die faces. And the bars for numbers 1 and 2 are twice the heights of those for bars 3 through 6. Clearly a non-normal distribution. To the right is panel B, which shows a distribution of the 500 sample means, and this distribution is actually very Gaussian looking. Back to the text. The histogram of the data in the population has a strongly non-Gaussian shape, but the histogram of the sample means has a Gaussian shape. In other words, the distribution of sample means is Gaussian, even though the distribution of the data is non-Gaussian. Let's see another, even more striking example. Here I created a data set that follows a power law distribution, which is clearly non-Gaussian. Then I drew 500 samples, each of which comprised 30 randomly selected data points, and created a histogram of those sample means. Again, the distribution of sample means is Gaussian, although the distribution of the data is not. This paragraph references figure 9.8, which shows a distribution of population data on the left and 500 sample means on the right. The overall organization of this figure is the same as figure 9.7, which I just described. Key difference is that the population data here have a power law distribution such that larger data values to the right of the x-axis have decreasing counts on the y-axis. Again, the important take-home message is that the population data is strongly non-Gaussian, but the distribution of the sample means is Gaussian. Back to the text. The law of large numbers and the central limit theorem make a powerful duo. As the sample size increases, or as the number of samples with small sample sizes increases, the estimate of the population mean becomes more accurate, and those sample estimates will be Gaussian distributed around the true population mean. Section 9.6.2, Central Limit Theorem, Part 2, Mixing Variables. There is a second implication of the central limit theorem, which is that the distribution of random mixtures of variables tends towards Gaussian, even if the individual variables are non-Gaussian distributed. Figure 9.9 illustrates this concept. I created 2 variables, a sine wave, called data 1, and uniform noise, called data 2. Data 1 has a distribution that is so non-Gaussian, it almost looks like an upside-down Gaussian. And data 2, of course, has a familiar flat distribution for uniform noise. But then, the 2 data sets sum together, literally the point-by-point summation of the 2 data sets, has a distribution that tends towards a Gaussian. This paragraph references figure 9.9. Figure 9.9 has 6 panels organized in 3 rows and 2 columns. In the first row, we see data 1 on the left and histogram 1 on the right. The data are a sine wave, wiggly line goes up and down over the x-axis, and its histogram is very strongly non-Gaussian. It has mostly flat histogram for most of the x-axis values, and then it very sharply goes up, corresponding to data values close to -1 and close to +1. Data 2 shows uniformly distributed noise, just looks like a rectangle of random dots. Its histogram is flat, plus or minus noise, as you would expect for a uniform distribution. Then in the bottom row, panel E, we see data 1 plus data 2. This just looks like a noisy, broad sine wave. And remarkably, its histogram looks not quite like a pure Gaussian, but more kind of triangular than either histogram 1 or histogram 2. Back to the text. This result of the central limit theorem is not trivially guaranteed. It depends on several assumptions, including the variables being in the same scale. To demonstrate the scaling assumption in figure 9.10, I use the same code, but scaled data 1 by a factor of 10. So the histogram of these summed variables is clearly non-Gaussian. This paragraph references figure 9.10, which shows that mixing and Gaussianity depends on the data scale. This figure is nearly identical to figure 9.9, which I just described, except that the sine wave is scaled up by a factor of 10, and therefore the summed data set, so data 1 plus data 2 in panel E, looks like a thinner sine wave compared to figure 9.9. Its histogram looks a lot less Gaussian. It's mostly flat, and then it has peaks going up on either side. Section 9.6.3, the distribution of sample means. The central limit theorem states that the sample means are normally distributed with mean mu and standard deviation SEM. In other words, when you compute the mean of a sample, that mean itself is drawn from a population of sample means. Mathematically, this is expressed as follows. Equation 9.4 reads x bar is distributed as normal distribution with mean mu and variance sigma over square root of n, where x bar is the sample mean, mu is the population average, sigma is the population standard deviation, and n is the sample size. Of course, you recognize that dispersion term as the SEN, the standard error of the mean. Scaling by sample size means that larger sample sizes will produce narrower sample mean distributions. Indeed, as n increases towards infinity, the SEM goes to 0, meaning that the distribution of sample means will equal the population mean. On the other hand, the equation predicts that the sample size doesn't affect the mean of the distribution, so the distribution of sample means will be centered on the population mean regardless of its dispersion. You will explore this empirically in exercise 6. Section 9.6.4, Implications of the central limit theorem. The central limit theorem is important for many reasons in statistics and signal processing. I will highlight a few of those reasons here. Estimating population means from samples. The central limit theorem, in combination with the law of large numbers, means that by pooling data over many samples, we get a good estimate of the population mean. This is used, for example, in market research, where small samples from many different stores or geographical regions can be combined. Assumption of normal distribution. Many inferential statistics rely on assumptions of Gaussian distributions, but many real-world data variables are non-Gaussian distributed. What to do? Well, if we use the sample means as the basis of statistical inference instead of the individual data values, then the central limit theorem guarantees that the normality assumption will be met. Footnote. Well, it's not really a strict guarantee because the central limit theorem depends on sampling being random and of sufficient size. Back to the text. This is also relevant for computing empirical confidence intervals, which you will learn about in Chapter 13. Demixing multivariate signals. In image and signal processing, multiple sources can be mixed together. Think of a microphone recording people talking, background music, and car traffic. An analysis method called independent components analysis is designed to separate or demix the sources and is based on the assumption that signals are non-Gaussian distributed while random mixtures of signals are Gaussian distributed. Section 9.7 is the exercises. I will not read these out loud. I encourage you to visit my YouTube channel where you can find the playlist corresponding to the discussion and solutions of these exercises. End of Chapter 9.